Okay, in this video, we're going to talk about polynomial and rational inequalities. Okay, and this is for my 11-10 class, and it's also for anyone that's interested in this video as well. In this section, we're going to talk about solving polynomial inequalities and solving rational inequalities. Okay, so let's define what a polynomial inequality is. So here we're going to start off with that. A polynomial inequality is any inequality that can be put in one of the forms. That is, either f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0. So it's got to have one of those four inequality symbols here. And your f of x is going to be a polynomial function. Okay. So now we're going to start off with a procedure for solving a polynomial function. So the first step is to express the inequality in the form of f of x is less than 0 or f of x is greater than 0, where in this case your f is going to be a polynomial function. So that means you're going to have to move some terms over to the opposite side in order to get a 0 on the right side of that inequality. And then you're going to solve the equation f of x is equal to 0. This is step number 2. You might have to do some factoring and then set each factor equal to 0 and solve for x. Those x values are going to be the real solutions, which will be your boundary points. And then number 3, you're going to locate these boundary points on a number line. Therefore, you're going to be dividing the number line into intervals. And then step number 4 is to choose one representative number. We call that a test value within each interval and evaluate f at that particular number. And one of two things will happen. If the value of f is a positive number, then that means your f of x will be greater than 0 for all numbers in that interval. Or if the value of f is negative, then that means that f of x will be less than 0 for all the numbers that are in that interval. And then the final step would be to write the solution set. You'll be selecting the interval or the intervals that satisfy the given inequality. Now this procedure is going to be valid if you've got less than being replaced with less than or equal to, or greater than being replaced with greater than or equal to. But you must include those boundary points in the solution set. And that's for less than or equal to, or greater than or equal to. Include your boundary points. Alright, so now let's take a look at some examples. Well, I'm just going to do a couple of examples on this video. Starting with this one. Here we're going to solve and graph the solution set of x squared minus x is greater than 20. So in this case, this will be x squared minus x is greater than 20. So the very first thing I need to do here is write this as either, in this case, f of x is greater than 0. In other words, I need to get a 0 on this side of this inequality. So I need to move the 20 over to where the x squared minus 20 is by subtracting 20 on both sides. So that means I'm going to have x squared minus x minus 20 is greater than 0. So I have it in the form of f of x is greater than 0. Now I'm going to solve this as if it was x squared minus x minus 20 equal to 0. This is what's going to help me find my boundary points. So in this case, I need to factor x squared minus x minus 20 into two binomials because I have a quadratic equation. So that x squared, I'm going to break that up as x and x. And I need factors of negative 20. That's going to give me negative x as a middle term. And I'll have to use 4 and 5. Now, keep in mind the larger of the two factors takes the sign on the middle term. The middle term is a minus, so that 5 has to be a minus 5. And the 4 will have to be a plus 4. So I get x plus 4 times x minus 5 equal to 0. And now I'm going to set each binomial factor equal to 0. So I get x plus 4 equal to 0. And then I get x minus 5 equal to 0. And then for each one of these, I'm going to solve for x. So for the x plus 4 equal to 0, that means x is equal to negative 4. And for the x minus 5 equal to 0, that means x is equal to 5. So these are going to be my boundary points on the number line, x equal negative 4 and x is equal to 5. Okay, so I'm going to draw a number line here. I'm drawing free-handed, so forgive me for that. So here's 0. Let's say negative 4 is to the left, and 5 is to the right. Now keep in mind, the inequality says strictly greater than 20, or strictly greater than. So that means these numbers will not be included, the negative 4 and the 5. So I need to draw an empty circle at negative 4 and an empty circle at 5. Now notice, those boundary points separate this number line into 3 different intervals here. Now I'm going to create a table here. The first column will have the interval that I will be dealing with. So here, if you look at this from left to right, the interval, this goes indefinitely to the left, so that's negative infinity up to negative 4. And I'm using parentheses. And then the next one will be between these two boundary points, negative 4 up to 5. And then finally, the last one will be 5 all the way out to infinity. Those are my intervals here that I'll be using in this particular problem. Alright, next will be the test value. I'm going to pick a value for x that falls within each one of those intervals. And for each test value, I'm going to find out what f of x is at that number. That's going to be the next column. Then the last column will be the conclusion to determine whether it is positive or negative. So I'm going to start with negative infinity up to negative 4. I'm going to pick a number that's within this interval as a test value. Let's try x equal negative 5. And then to find out what f of x is, by the way, since I got a 0 on this side, whatever's on the left of that inequality symbol, that is what f of x is. In this case, that x squared minus x minus 20 is what f of x is. Very important. Because I'm going to substitute negative 5 in for x in that f of x function. Now if you want to, you can use your calculator if you like. But since it's negative, I need parentheses. Negative 5 and then close parentheses. That's squared minus negative 5 minus 20. That's going to give me 10. So at x equal negative 5, which is my test value, f of x came out to be 10. And 10 is a positive number, so that means for all the values of x between negative infinity to negative 4, the values of f of x will be positive. So I write the word positive there for that interval. And now for -4 to 5, that's this interval right here, a good test value for that would be x equals 0. So try to use x equals 0 whenever you can as a test value. So when x is 0, this is going to be 0 squared. Oops. 0, and that's squared, not -1. I want that to be squared. Okay. Start over. 0 and then x squared for the square, minus 0 minus 20. That's -20. And 20 is negative, so that means from -4 to 5, the values of f of x will be negative. And then from 5 to 5 to infinity, that's this interval out here, I need a value for x that's within that interval. So here, I'm going to pick x equals 6. Now keep in mind, I could have picked x equals 7, 8, or I could pick 15, but as long as I select a test value that falls within that interval, that's fine. But for simplicity, I'm using x equals 6. Then I'm going to substitute each x in f of x with the 6. So here, this will be 6 squared minus x, which is 6, minus 20. That also gives me 10. So in this case here, I get 10. And it's a positive number, so I'm going to write down the word positive. That means for all the f of x values within the interval 5 to infinity, those values will be positive. Okay? Now, let's look at this here. This inequality says greater than 0. Anything greater than 0 means positive. So I need to select the intervals that gave me a positive conclusion. That's going to be the solution set. And it's going to be this one and this one that I'm checking off. As you can see here. So now, the solution set for this polynomial inequality will be this: -infinity to -4, or from 5 to infinity. And notice I'm using parentheses here because my inequality is strictly greater than. That means I need to use parentheses because those boundary points are not going to be included in the final solution set. Now we're going to graph that solution set on a number line. So here's -4, and this is 5. -4 is not included, so I'm going to draw a right parentheses at -4 like this. And -infinity is off to the left, so I shade to the left like this. And 5, I'm going to use a left parentheses to indicate that is not included as well. And I shade indefinitely to the right like this. So that's what the graph of the solution set looks like for that particular problem. Okay. So that was example number 1. Okay, do not worry about example number 2. So we're going to omit that because that is not in the homework. Okay, so don't worry about example 2. Alright, let's look at example 3. In this case here, we're going to solve and graph the solution set, which is x plus 3 times x minus 5 is greater than 0. So here this is again strictly greater than. That means that my endpoints are not going to be included in this solution set. And notice in this case it's already factored for you, so you don't have to worry about trying to find factors here. It's already factored completely. So what we can do here is find out what our boundary points are by letting x plus 3 times x minus 5 be equal to 0. And then we're going to set each binomial factor equal to 0 since it's already factored completely. So this means I have x plus 3 equal to 0 and x minus 5 equal to 0. Each one of these we're going to solve for x. So for the x plus 3 is equal to 0. If I subtract 3, I'm going to get x is equal to negative 3. And for the x minus 5 equal to 0, you're going to get x is equal to 5. So these are the boundary points I'm going to be using here. X equal negative 3 and x is equal to 5. So I'm going to draw a number line over here to the right side of this paper. So you got 0 in the middle, negative 3, and 5. Again, I'm going to draw empty circles here because those boundary points are not going to be included. And that separates the number line into 3 different intervals here, as you can see. So, starting with the interval, I'll list each one of those. Starting from left to right. This is from negative infinity up to negative 3. And then the next interval from negative 3 up to the other boundary point, 5. And then the last one will be from 5 all the way out to infinity. Okay? The next column will be the test value that I will select. And then my f of x. And then the conclusion. Now, since I do have a 0 here, this right here represents f of x. So that f of x would be that x plus 3 times x minus 5. So if you have a 0 on the right side, then what's on the left side represents f of x. Alright. So, for each interval, I'm going to select the test value. So, starting with negative infinity to negative 3, I'm going to pick a test value within that interval. I'm going to pick, let's say, negative 4. I can use negative 5, negative 6, or negative 7, but as long as you select a test value that falls within that interval here. And then I'm going to substitute each x with that negative 4 here. I'm going to use my calculator for this. So I'll clear this out. I'm going to do left parentheses, substitute the x with negative 4, so it'll be negative 4 plus 3, close parentheses, and then left parentheses, negative 4 minus 5, close parentheses. I end up getting 9. So f of x is going to be 9. And 9 is a positive number, so that means for all the values of x within this interval, negative infinity to negative 3, my f of x values will be positive. And then next for negative 3 to 5, that's this interval right here, I'm going to use x equals 0 as a real good test value. So we'll use that. And then substitute 0 in for x. So left parentheses here, that x will be 0 plus 3, close parentheses, and then left parentheses, this x will be 0 minus 5. I ended up with negative 15. Negative 15 is a negative number, obviously, so between negative 3 and negative 5, the values of f of x for that function will be negative. And then finally, for 5 to infinity, that's this interval right here. I'm going to pick, let's say, x equals 6. I can use 7, 8, 9, 10, as long as those values are within that interval, 5 to infinity. So I'm going to substitute 6 in for x. Substitute the x with 6. So it'll be 6 plus 3 in parentheses, and then another parentheses, 6 minus 5. That also gave me 9. And 9 is also positive, so all the values of x from 5 to infinity will be positive. Now here I need to select those intervals that gave me a positive conclusion. And that's because greater than 0 means positive. Okay? So it has to be these two right here. Now had it says less than 0, then I would have selected the one that says they gave me a negative conclusion, negative 3 to 5. Okay? So now, my solution set for this inequality, or polynomial inequality, would be the ones that gave me a positive conclusion. Negative infinity to negative 3, and from 5 to infinity. And then the graph of that solution set would be this. Here's negative 3, and there's 5. Now it says strictly greater than, so my endpoints are not going to be included. Had it said greater than or equal to, then those endpoints would be included. But here, they're not going to be included. So at negative 3, I need a right parentheses there. Negative infinity is off to the left, so I shade to the left indefinitely. 5, I use a left parentheses there. And infinity is off to the right, so I shade to the right indefinitely. So that's what the graph of that solution set for that polynomial inequality looks like. Okay? Alright. Let's talk about rational inequalities. Now we've already did graphing of rational functions here. And we dealt with rational equations and, finding the domain of a rational function as well. So now, rational inequality is going to be any inequality that can be put in one of the following forms. And that is f of x is less than 0, or f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0, where f, the function f, is a rational function of the form f of x equal to p of x divided by q of x. That's just a quotient of two polynomial functions here, p of x and q of x. Okay? Now, the procedure is almost the same. The first two are different, but when you get to steps 3, 4, and 5, they are exactly the same as if you were solving a polynomial inequality. The first step is to bring all the terms on one side, obtaining a 0 on the other side. And you may have to express the rational function as a single quotient. That may mean you might have to get a common factor for those two. Then number 2, you're going to set the numerator equal to 0 and the denominator equal to 0. And then steps 3, 4, and 5 are exactly the same. Basically, you're going to find out what your boundary points are and place them on a number line. And then number 4, you're going to pick a test value to determine whether it's positive or negative for that test value. They'll tell you that for that interval, it's either going to be positive or negative, and then you're going to select the solution set that will satisfy that particular inequality. Now, here's the important thing you need to know. In a rational inequality, you are to avoid any values of x that will make the denominator 0 in your solution set, because we should know by now that dividing by 0 is undefined. That's very important. So like in this example that we're going to do here is this. Here we're going to solve and graph the solution set of x minus 6 divided by x plus 2 equal to 0. Well, greater than or equal to 0. Now, let's take a look at this here. It's already a single quotient, so we don't have to worry about trying to find common factors here. And we already got a 0 on one side of this inequality. So, step number 1 is already taken care of. Now the next step is to set the numerator and the denominator equal to 0. So we're going to set x plus 6 to be equal to 0 and this should be x minus 6. X minus 6 equal to 0 and x plus 2 equal to 0. Each one of these we're going to solve for x. So for the x minus 6 is equal to 0, we're going to have x is equal to 6. And then for the x plus 2 is equal to 0, I have to subtract 2. That would mean x is equal to negative 2. These are your boundary points here. X equals 6 and x equals negative 2. So the next step would be to put this on a number line. Now we have to think about this. Which one of these boundary points will give us a 0 in the denominator? And if you look at it, it's going to be the negative 2, because negative 2 plus 2 will give me a 0 in this denominator. So at negative 2, I have to place an empty circle there, because I'm going to get a 0 in the denominator at x equal negative 2. But at 6, since it says greater than or equal to 0, I can put a closed circle there, because I won't get a 0 in the denominator at 6. Now, again, my number line is separated into 3 intervals from those boundary points here. Okay, so now, let's identify what our intervals are going to be. From left to right, negative infinity up to negative 2. And then the next interval will be from negative 2 up to 6. Then finally from 6 all the way out to infinity. Those are my intervals here. Next, I need a test point. Next, I need my f of x, and then conclusion. Okay. Since I already got a 0 on the right side, that x minus 6 divided by x plus 2, that's f of x. So I'm going to write down what f of x is, actually. Okay. So now, let's pick a test point from negative infinity up to negative 2. That's this interval right here. I'm going to pick x equal, let's say, negative 3. That's in the interval. And then I'm going to substitute each x in f of x with negative 3. So I'm going to use my calculator for this. Clear this out. The numerator and the denominator I'm going to put in parentheses here. So it'll be left parentheses, I'm substituting with negative 3, so it'll be negative 3 minus 6, close parentheses, divided by, left parentheses, negative 3 plus 2, close parentheses. I end up getting 9. And it is a positive number, so that means for all the values of x within that interval negative infinity to negative 2, I'm going to get positive f of x values. And then for negative 2 to 6, that's this interval here, I'm going to use that x equals 0 as a good test value for that. Then substitute 0 in for x here. So it'll be left parentheses 0 minus 6, close parentheses, divided by left parentheses 0 plus 2, close parentheses. That'd be negative 3. And it is negative, so that means from negative 2 to 6, all the values of f of x will be negative. And then finally from 6 all the way out to infinity. I'm going to pick, let's say, x equals 7. So I'm going to substitute 7 in for x. So it'll be 7 minus 6. 7 minus 6, close parentheses, divided by, then left parentheses, 7 plus 2, close parentheses. Here I'm going to get a decimal of 0.1 repeating, but that's okay. Sometimes you might have that. But anyway, if you look at it, it is a positive number, so that means from 6 to infinity, all the values of f of x within that interval will be positive. Okay? Now it says greater than or equal to 0, so that means I need to select conclusions that gave me a positive conclusion here. Intervals that gave me a positive conclusion. That would be this one and that one. As you can see. So, the solution set for this rational inequality will be negative infinity to negative 2. Now keep in mind I'm using the parentheses here because at negative 2 I will get a 0 in the denominator. Now I can use a 6. So I'm going to use a bracket at 6 all the way out to infinity. And now the graph of that solution set looks like this. Let's see, negative 2 is here, 6 is here, and in this case here, at negative 2, I'm going to use a right parentheses there. Negative infinity is off to the left, so we shade indefinitely to the left, like this. And then 6, we use a bracket at 6 because 6 can be included. And we shade indefinitely to the right. So that's what the graph of that interval would look like for this rational inequality. Okay. All right, here's another example of a rational inequality. And that will be the last one I will do in this video here. Here we got x plus 5 divided by x plus 2 is less than 0. Now this is strictly less than. So it's already it's already a single quotient. So I don't have to worry about trying to make it a single quotient, and I've already got the 0 on the other side. So I can go ahead and set the numerator equal to 0 and the denominator equal to 0. So I'm going to set, let's see, x plus 5 equal to 0 and x plus 2 equal to 0. Each one of these I'm going to solve for x. So for that x plus 5 is equal to 0. Let's see, if I subtract 5, I'm going to get x is equal to negative 5. And then for the x plus 2 equal to 0, if I subtract 2, that means x is equal to negative 2. So these are going to be my boundary points on the number line. Let's see. Now they're both negative, so I know negative 5 is going to be over here and negative 2 is going to be closer to 0. Now this says strictly less than. So I need empty circles at both negative 5 and at negative 2. even though negative 2 will give me a 0 in the denominator, I have to put an empty circle there. But for negative 5, it says strictly less than, so negative 5 will also have an empty circle there. Now this is separating the number line into 3 different intervals here. So let's start off with interval. Let's identify those. From left to right, they'll be from negative infinity up to negative 5. The next interval will be from negative 5 to negative 2. The last one will be from 2 all the way out to infinity. Okay. Then next will be my test point. And then finally, f of x and the conclusion. Alright, I've already got a 0 on the right side, so what's on the left side is f of x, which is in this case that x plus 5 divided by x plus 2. Alright, now for each interval, I'm going to select a test point. So here, I got negative infinity to negative 5, that's this interval right here. A test point will have to be something like x equal negative 6. X equal negative 6. And I'm going to substitute negative 6 in for each x in the f of x function. So again, I'm going to use my calculator here to do that. Clear this out. So here, left parentheses, negative 6 plus 5, close parentheses, then divided by, and then left parentheses, negative 6 plus 2, close parentheses. And in this case, it came out to be a decimal of 0.25. That's okay. It's positive, so that means for the interval negative infinity to negative 5, all the values of f of x will be positive. Then the next interval will be from negative 5 to negative 2. That's this interval right here. You want to be careful of what values you want to pick. It's got to be within that interval. And I'm going to say, I'm going to say negative 3. I could use negative 4. They're both within that interval here. I'm going to use x equal negative 3. And substitute negative 3 in for each x in f of x. So, left parentheses, negative 3 plus 5, close parentheses, divided by, left parentheses, negative 3 plus 2, close parentheses. This ended up being negative 2. And it is negative, so that means all the values of f of x within the interval negative 5 to 2 will be negative. And then finally 2 to infinity. Well, if you look at 2 to infinity, it contains 0. So I'm going to use x equals 0 as a test point. And then substitute 0 in for x. Well, left parentheses, 0 plus 5, close parentheses, divided by, then left parentheses, 0 plus 2, close parentheses. That will give you 2.5, which is of course a positive number, so that means all the values of f of x from that interval 2 to infinity will be positive. Okay? So now we're going to select the intervals that satisfy that rational inequality. Well, in this case here, less than 0 means negative. We need to select the intervals that gave us a negative conclusion. There's only one, and that's this one right here. The interval was from negative 5 to negative 2. So that means the solution set for this rational inequality would just be negative 5 to negative 2. So now the graph of that solution set, well, that's over here, -5, -2, is strictly less than. So that means I have to use parentheses at -5 and at -2. Left parentheses at -5, right parentheses at -2. And I'm going to shade in between the two, like this. So there you have it. That is the graph of the solution set for that rational inequality. Okay. Now, the last example we will omit because that's not in the homework, and you will not be held responsible for that one, so we're going to omit that as well. Okay? So that's going to complete this video on polynomial and rational inequalities. Now, the homework is going to be available for you to complete on my MATLAB for this particular section. If you have any questions, feel free to email me if you need to. Okay? This video will be on Canvas and it's also on my MATLAB, so watch this video as much as you need to. Okay? Because even though this is not going to be on the third exam, keep in mind I will be emailing you about what your third exam will be. Okay? So do be prepared for that.